Ladies and gentlemen, thank you for your valuable time to attend our presentation. It's my pleasure to present a robust 3nm to 350nm design flow using Silvaco tools during the 2022 surge. In this talk, I will introduce silicon creations with a few overviews. Then, we will describe the challenges we face in the IP industry. Lastly, I will conclude our collaboration with Silvaco from our front-end design to the back-end design. Instead of providing a GDS product, we will also describe how the robust silicon was developed using the Silvaco tool efficiently. We have been providing clocking IPs to our fabrics IC customers since 2006 and have been growing consistently since 2010. As you can see from the graphic of customers by region, we have design centers in Atlanta, USA and Krakow, Poland. Our design engineers understand the main mission is to help our customers get to market quickly, and they have recognized our quality and support with multiple Best of awards. Therefore, we have over 330 customers in the world, including over 130 customers in China. Our customers ship using our IPs are volume production from 180nm down to 5nm FinFET. Our 3nm PLLs are silicon proven already. Silicon Creations supports 12 foundries so far, including many geometries and flavors. We use Silvaco tools in our current work from 3nm to 180nm, including multiple foundries as shown logo here, and the process variants such as planar CMOS, FDSOI, and FinFET. The core of our PL product is the general purpose functional synthesizer, which is so widely programmable. We have used it in hundreds of chips and a wide variety of markets. This has resulted in some truly gigantic volume. For example, in TSMC 28nm, 12nm, and 16nm FinFET, over 200 production chips using this IP, which has resulted in over 2 million wafers delivered to customers with our PL IP. This kind of volume are a testament to our robust, high-yield design and customer support. To provide more functionality, functional complementary RTL like expression clock generator, SSCG, jitter cleaner, and anywhere alignment are available. Last, we will leverage the high-volume design to make PL variants that are optimized for low area, low jitter, low power, and high speed up to 10 GHz. Our latest new digital LC PL can even achieve 50 times better figure of memory, FOM. Again, our PL IPs are available from 180nm down to 3nm FinFET. Our 3nm silicon is being tested now, and its performance matches simulation. SerDes is one of our key product line, and we focus primarily on the PMA, the high-speed error part, including the serializer, line driver, line receiver, equalization, CDR, and De-serialization. Our SerDes has enabled extremely good performance in the micro-semi FPGA and very low power due to the robust architecture, which provides a very low risk. Over the past few years, we reported and proven this multipolar PMA to several mainline process nodes from 180nm down to 6nm with a data rate ranging from 100 megabit per second up to 33 gigabit per second. We have over 75 different SerDes IP in production, or currently in development with a wide and diverse customer base. Besides our multi-protocol PMA, we have protocol-specific PMS built for V/1, DisplayPort, JST204, FPD-Link, and several customer interface and ultra-low latency PMAs. Besides our PLLs and SerDes IP, we may have other handy analog IP that function complementary or use core components. For example, SerDes IO buffers may have plain RX, TX, and mostly bidirectional variants, including CMOS IO buffers. The free-running oscillator is for PL reference clock. We have a quick clock generator down to the nanosecond and a delay to digital converter DDC for dynamic frequency scaling DFS application. Then we also have the clock distribution IPs, such as CMOS buffers and MUX, to mitigate the excessive accumulated jitter in your SoC system. For your chips, a few building blocks like the bandgap and power on reset POR are also available. This example shows you can find our IP in TSMC database online. Just from the top 10% of our products, there are over 10 million wafers and 575 chips shown in the records. Let's go through the challenges we face in the IP industry and our cooperation with Silvaco. For most front-end designs, IP vendors will face unique front-end design challenges. For example, we face tape-out in different processes each week. Therefore, we may need a foundry and process-independent front-end design method. Using Silvaco tools like Gateway help us solve problems with multiple processes and technology nodes, and I will present it. Starting the schematic design, we have a foundry and geometry independent schematic flow using Silvaco's Gateway, which allow all the schematic to be shared across all projects in different process nodes. For example, our frictional PL shares schematic from the top down to gate level from 180 nanometer down to 3 nanometer. Only transistor level schematics are unique and carry device size and model type information. This foundry and geometry independent schematic flow, allowing porting from process to process quickly with very extremely low risk. Let's look at the front-end design example of two extreme cases: 28nm plain CMOS and 3nm FinFET. In FinFET, angle design is still the same and at a high level, not that much has changed. Again, the angle block still lives at 5nm or even down to 3nm. However, statistical variability is increasing as device shrinking, so more monocolor runs are a must. In addition, schematic simulation of a high-speed block would deviate from post-layout reality, especially parasitic resistance, made it much more post-layout verification and work. Therefore, back-end design challenges faced by IP vendors are more difficult than the front-end challenge. For example, our 3nm and 180nm schematics are very similar in the front end, but the back end is very different. Our back-end design flow is based on Silvaco Expert that addresses these challenges, which we will present it. Before that, I'll present an overview of the process complexity and scale. A simple measure of process complexity is the number of GS2 layers in the PL IP, even though the PLs compare use only up to layer metal 4. The number of GS2 layers of 5nm has increased 9 times since 180nm, showing an increase in complexity. But does the 9 times increase reflect process complexity? We agree. In the past decade, process technology has gotten increasingly complex, But how? Another simple and not very accurate measure of the process capacity is the design rule manual DRM thickness. From 180 nm to 3 nm FinFET, the DRM thickness has increased over 4 times, and the 3 nm will keep growing before maturity. Does the big increase in DRM thickness show the process capacity? The last measure of the process capacity is straightforward by the runtime of the design rule check DRC. From 180 nm to 65 nm, the DRC runtime and process capacity were increasing modestly for IP blocks. The 40 nm and 28 nm nodes saw a large increase in the number of checks and the capacity of the checks, and hence the DRC runtime. But the FinFET design is a whole order of magnitude more complex because several factors. First, tighter, more complex rules. Second, more field geometries. Lastly, more layers, for example, GDS2 layers, derived layers, mark layers, etc. Therefore, we can recognize the 5 nm FinFET runtime are over 10 times the 28 nm runtimes and nearly 100 times the 65 nm runtime, which are quite complex and quite expensive in IP development. There is some debate over whether the process scales anchor circuits well or not. The plot shows the area for silicon creations PLLs with similar frequency and jitter spec from 180 nm to 3 nm. We can see the PLL size decreased to nearly 10 times and benefit to low cost for sure. If we hold the noise constant, ballpark KT on C, the area should scale with the capacitance area, and it does. For example, the gate capacitance was scaling through 65 nm, but the metal-metal capacitance is dominant below 40 nm and still scaling well. So, the scale of the algo function, but very well as the digital function. A simple comparison demonstrates that the digital scaling from 180 nm to 3 nm is 300 to 1, but the algo scaling from 100 to 3 nm is only 10 to 1. Let's switch to our layout design flow with 3 nm to 180 nm as an example here. Our internal developed and process independent layout flow allow building blocks to be shared between foundries. In addition, here the 3 nm and 180 nm layouts of the same section of IP show the shared platform. The process independent flow is owing to the PLLs and scripts being developed internally in Silvaco Expert to avoid foundry-provided, foundry-specific PDK with foundry IP. Then, the PLL can be used with adjustment for scaling to pass the design rule manual DRM from 180 nm down to 3 nm. Specifically, we use the stream mapping file in Expert to create foundry-specific GDS, for example, TSMC versus UMC versus SMIC. The general IP cell strategy is highlighted here. First, the layout of the device involves many DRC rules. Therefore, different size devices involve different rules, and that takes a lot of time to draw and verify. Second, the PLLs significantly shorten the user's time. Lastly, FinFET devices require many parameters, W, L, N, number of things, and so forth. Therefore, the scripting in Silvaco Expert could be useful to save lots of time. There are two scripting languages possibility. The first one is called Lisa, and it's useful in the design of a simple structure like vias and planar FET. Therefore, the second one, called JavaScript, would be needed in the design of complicated structures. The object-oriented design enables the creation of complicated FETs, resistors, multi-fin structures, and so forth. In this example, we will create PMOS 1.8 volt device, which has the following parameters. To place the P cell in step 1, we should select P cell type to be the transistor. Step 2 would be set those required parameters and the type of the MOS. Step 3 is to add context to the gate and gate vias by selecting the right Boolean values. The last step is to add source drain vias, dummy poly, PP, OD18, and unveil layers by selecting the right value. After the preliminary GTS is ready, we need to do the IP simulation and verification. Since silicon creations provide PLLs and SerDes IP, this mid-signal IP takes longer simulation time. In addition, we are simulating process from 3 nm to 180 nm, so we need a flexible design flow. Lastly, in advanced nodes like FinFET, the RC simulation is necessary to capture the real silicon performance. So we will discuss the PL and SerDes simulation. Then, the difficulty faced with the RC simulation will be discussed. In SerDes simulation, the most obvious and critical difficulty is its diverse time scales, which present a challenge for simulation in 10 orders of magnitude. For example, first, jitter requirements are on the order of hundreds of femtoseconds. Second, bit rates are on the order of 100 picoseconds. Third, word rates are on the order of 10 nanoseconds. Fourth, AC coupling time constant on the order of a microsecond. Fifth, PL lag time on the order of 50 microseconds. Lastly, link behavior on the order of a millisecond. In a PLL SPICE simulation, we could have another rough observation to get a sense of its simulation difficulties. In 1996, a PLL designer may preset the loop filter voltage and still need 3 weeks for a schematic lag simulation. In 2001, we still need 1 week for a schematic lag simulation. In 2006, 3 days for a schematic lag simulation. In 2011, a few days for a iterated lag simulation. In 2016, we can kit off a bunch of iterated lag simulation and check the result the next morning. In 2022, we kit off a bunch of RC iterated lag simulation in 6 nm and below, but we still need a few days for the iterated lag simulation because the increased process complexity faster than the simulation speed. Let's go through the SerDes system overview. The PMD, PMA portions of the SerDes are part of a bigger C-Link system. The SPICE is still the key verification tool for the PMA, PMD, which is shown in the dash box, and we will focus on this talk. But to model functions above PMD, PMA levels like the PCS and controller, the SPICE is no longer a good tool. Instead, a good value model is a must. Therefore, for system verification, a value model of the SerDes is a must and useful in quickly testing the full PMA functionality, all operating modes, and combinations. Fortunately, Silvaco Silos is a good tool for digital simulation coverage. Silicon Creations has proprietary modeling flow for generating value models of mixed-signal circuits from the LVS Netlist, so we can guarantee gate-level accuracy versus schematic. The Verilog model could capture needed angle functions using difference equation and is compatible with digital verification. Let us go through and dive into our Verilog modeling flow. A SPICE Netlist can be generated from the schematic database through Silvaco Gateway and the Netlist matches the layout from the LVS check. Then our SPICE 2 Verilog Netlist parser can generate an accurate Verilog model. So the abstract Verilog model are made of the lowest level left cells and will be verified against SPICE. Moreover, we can include noise by using the Verilog $ random function, and the RTL can be used for major digital blocks. The Verilog model result cross-match SPICE, and the fast speed allows all critical operation modes to be verified. This angle modeling in Verilog example show a second-order PLL loop filter model in Verilog. First, we convert the angle nodes into n-bit buses. Second, the discrete time difference equations are used instead of differential equations in SPICE. Lastly, we not only can make the Verilog result arbitrarily close to the SPICE one, but we also enhance the speed. We can show another Verilog model of a SerDes system modeling in the mixed-signal circuit. The complete SerDes channel locking from start with spread spectrum TX clock and 0.4 UI sinusoidal jitter added to TX data to further test the RX jitter tolerance (J-tau) verification through the loopback configuration. Therefore, the whole system brings up in sequence starts the power on, then the PL will lock, and we send the TX data with the embedded spread spectrum and sinusoidal jitter to the RX. Since the RX would need a settling time to lock to the TX input data, you may see a few RX bits. The error counters will show errors initially, and then the RX clock data recovery CDR will lock, and error-free showing in the RX bits error counter. The whole SerDes TX loopback to the RX only runs in seconds on one core simulation machine, which is very impressive owing to the simple modeling. In SPICE simulation, second question also uses a proprietary internal simulation flow, and we will show a few steps of how the flow was running. First, the simulation flow starts with schematic test bench and data shared across process and geometry. Our in-house scripts allow permutation and variation of SPICE stacks and link with the Open GUI engine for parallel simulation. There are over 3,000 core simulation farms used, allowing rapid simulation over process, voltage, temperature, and mismatch. We use SmartSpice from Silvaco, AVES from Mentor BDA, PointSim, and Spectre RF as SPICE simulator with foundry SPICE model files. If we recall a few slides earlier about the SerDes timescales difficulty, all the waveforms here are showing the various timescales result that can show our flow with Silvaco tool that could mitigate the difficulty in SPICE. We show a few examples here. First, a 16 GHz lock simulation showing 24 microseconds of simulation time at 32 gigabit per second with 1 bit duration equals 31.25 picosecond, which is a huge timescale difference. Second, a 32 gigabit per second TXI diagram with thousands of bits with a time step accuracy of much less than 1 picosecond. Third, a DFE, CTLE plus channel simulation, including an S-parameter model for a 36-inch channel. Fourth, a fixed domain simulation of the whole TX for its return loss verification up to 32 GHz. Let's switch the gear to the backend related difficulty, interconnect challenges. The law of iteration and post-iteration simulation is becoming more important because the interconnect resistance is climbing quickly. For example, from 40 nm to 3 nm, the relative wire resistance ohms per square has risen almost 9 times. Therefore, the impact of resistance is leading to multiple challenges. First, the designs are becoming limited more and more by wire performance. Second, the designs are increasingly difficult to verify because of a need for simulation of distributed RC parasitic. Since in advanced process, we must take the interconnect resistance into account. The effect of interconnect on simulation time is tremendous. For example, the simulation time from a schematic simulation of a cap iterative sim is 2 to 3 times, but the simulation time from cap only to RC is another order of magnitude. There are a few implications of a long RC simulation time. First, longer development cycles. Second, need for more simulation license. Third, need for parallel simulation license. Fourth, higher development cost. Again, the simulation of interconnecting plus device is expensive, so we must do something. Any idea? Correct. We need to simplify the complicated RC netlist by any RC netlist reduction method, such that the simulation time and cost can be reduced through the RC reduction. But we must watch out for accuracy. Fortunately, RC reduction can often be done with little impact on precision. The goal is to speed up the simulation with a lower cost while maintaining reasonable accuracy. So, we can use the corner spread as a reference for accuracy. For example, if the corner spread is 40%, a full RC versus RC reduction accuracy does not need to be much less than 1%. To effectively reduce the RC netlist, Silvaco's Verilog provides great simulation time reduction while maintaining reasonable accuracy. In the 6nm FinFET example, the various reduced versions of the RC netlist are compared for the simulation with very close accuracy. We apply a whole TX as a test circuit in the RC netlist simulation. To benchmark, we also apply another vendor's RC reduction netlist as the gold standard. Our benchmarking results show that with Verilog's RC reduction netlist, we can speed the simulation up 5 times faster with a deterministic jitter error of less than 300 femtoseconds, or less than 1%, which was limited by the simulator's time step of 33 gigabit per second eye diagram. For circuits that are sensitive to mismatch, Silvaco provides a high sigma analysis tool. In the example below, we analyze the PL static phase offset SPO. The SPO is a key PL parameter since it's a component of a reference spur. We can show the SPO to be 20 picoseconds at 1 sigma, and then we can also analyze the results at 2 sigma, 3 sigma, or even over 4 sigma with statistic confidence. We can analyze the relative impact of different devices to help improve performance efficiently. To iterate the phase noise or jitter quickly in a PL, Silicon Creation uses a proprietary MATLAB-based frequency domain phase noise model to calculate the phase noise and jitter. The noise model includes all major noise sources, including VCO phase noise, reference noise, charge pump noise, divider noise, etc. in a PL. The plot shows the simulated and measured result difference are within 10%. We have tested the model of process and even different VCO topology, like LC and rim PLs, with excellent agreement. Besides standard electromigration EM tool, we also have internal EM flow that works with SmartSpice major statements. The EM information is read from foundry iteration decks, and the results are processed and can be viewed in expert easily. This is another useful tool to allow us to improve the EM performance in a layout quickly. Lastly, and most importantly, quality assurance QA is a must for delivering IP. Silicon Creation has a QA flow that works with Silvaco's EDA views and our generative views to ensure IP quality. Let's summarize and conclude today's talk. We went through an overview of Silicon Creation, and we have provided the role of an IP vendor. We've addressed the front-end challenges and solutions, including our use of gateway in mitigating porting challenges. Then we also talk about the back-end challenges and solutions, including our use of expert. Lastly, we spend lots of time discussing the mixed-signal design simulation challenges and solutions, including our use of SmartSpice, Verilog, silos, and variation manager. Hopefully, this talk may provide you with a few ideas of how we apply a robust 3nm to 350nm design flow using Silvaco tools. Thanks for your attention. For more information, please contact sales@siliconcr.com.